When you don't have diversity in the creative process, you inevitably end up with a single, narrow perspective in the output. This is Hannah Fry, a mathematician I follow. This is only to say how the inputs dictate the outcomes of an effort or an enterprise. Functions are the mathematized input-output converters, a relationship between inputs and outputs that is definite. Of course, not all relations are functions, mathematically speaking. Let us dive in and explore the ever-important world of functions. As a relation, that is, as a set of ordered combinations of elements. Functions relate a set of inputs to a set of outputs. The simplest of functions is the length to area relationship of a square, the way area of a square changes with changes in the length of the sides. In fact, all such formulae are functions. However, before we take off with functions, let it be added that functions may well be seen as the name of a class of relations that are particularly useful in quantifying behavior of changing situations or things, assertively linking the state of inputs to the changes elsewhere. Functions are relations that act in a way such that inputs always relate to exactly the same output at all times. Of course, till the relation is unchanged. Every input has its own output. Functions kind of processes the inputs to produce an outcome. Functions are one way of witnessing input to output, but multi-way output to input. The output is distinct to inputs, but not unique to an input. For example, -2 squared will always be 4, just as +2 squared will always be 4. There is only one pathway for -2, and that is to 4. One pathway for +2, also to 4. However, if we look back from 4, we could get to -2 or +2. In a function, thus, one or more inputs can have the same output. The output is not unique for unique inputs. The output is certain, definite, but not unique. Perhaps the most powerful feature of functions is that they are seamless converters. That is, input and output could be very distinct quantities. The picture shows a few such conversions, such as a function converting the strength of a force to a measure of the change in acceleration of a body in motion. In general, technologies and innovations invariably use functions. All kinds of system controls are functions. For example, circuit cutoff due to higher than threshold temperature in some process or equipment is an example of a function that takes temperature as input and outputs a mechanical cutoff action or an electrical impulse that cuts off the circuit. Functions translate dynamic, real-world situations and conditions into mathematical expressions. The interest rate formula is a function that relates principal interest rate and tenure to the interest amount over the tenure. It outputs the exact amount of interest for changing amount of principal, interest rate, and tenure of loan or deposit. In what is truly a powerful mathematical characteristics, functions can also work in the reverse. The inverse of functions are as powerful mathematical tool as the functions. For example, if the area of a square is a function that takes length of a side as input and outputs the corresponding area, then the inverse of the area function will take area as input and give the length as output. But -3 is not a valid length of a side and ignored. Both the function and its inverse are true for all positive real numbers. Interestingly, the inverse of a function need not be a function. For instance, a function that squares the input numbers does not remain a function in its inverse form. That is, the inverse function that square roots input numbers will give two numbers as output, one positive and another negative. Two outputs for the same input is a violation of the norms of being a function. And you are right. The inverse of an inverse function exists. It is the function itself. Let us now explore how functions are expressed. Like relations, functions can be visualized. In the picture, x square function is shown as a relation of set x and set y. Set y has elements that are square of the elements in set x. Visually, a function could be a diverging array of arrows, charts, connections, that is, many to one, besides one-to-one input-output relations. Functions could be tabled, put out as rows and columns of data. The picture shows two sets, one of students and the other of the marks obtained by them in an exam, in a tabular form. This relation of the two sets that connects the individual students to their marks is a function. Visually, a function has all different elements in the first set. The second set may have the same elements, such as 67. But a second relation that connects marks to students is not a function. Visually, non-functions show two or more elements in the first set that are the same. In the picture, 67 is awarded to two students. Thus, the single marks, 67, could result in either Ashi and Chen as the student awarded 67. This leaves uncertainty over the outcome of 67, and that is not a characteristic property of functions. Thus, when expressed as a table, functions must not have same input entries for different output entries. Much like relations, functions can be graphed, and we can figure out from the graphs if they represent function or a relation. We will picture two graphs, two non-function graphs. For educative purpose, it makes more sense to display graphs that show what functions are not. The first graph shows the function x equal to y square. If vertical lines are drawn over it, parallel to the y-axis, each line will touch the graph at two places. This would indicate two values for every value of x for the function, that is, two outputs for the same input value. Hence, the graph does not represent a function. The second graph has the same features. It also does not represent a function. This use of vertical lines at x equal to a to test for the existence of functions is called the vertical lines test of functions. Here, a is any point on the x-axis over the graph. Last but not the least, equations are used to represent functions. In fact, equations are the most popular way to capture and write functions. In the examples, there is an equation that is a function, y is equal to 2. And there is an equation that is not a function, x is equal to 2. Given that we know the vertical test of functions, it is easy to see why x is equal to 2 is not a function. It may be reiterated that x equal to 2 is not a function, but it remains a relation. Recall, relations do not demand definite same output for a given input. Another feature of functions that is due to the DNA that they share with relations is the existence of two sets, the first set and the second set in a relationship. In functions, the two sets are distinctly named. The first set is called the domain of the function. For example, the domain of the function 1 by x is all real numbers except 0. And the domain of the function log x is all the numbers greater than 0, that is all positive real numbers. The logarithm of a negative number is undefined. Domain is all the possible values the input can be or the values they can acquire, all that the function can work upon. It may help to recall that the first set in a relation is kind of the base or the boundary of the specific elements in relationship between the two sets. For example, the relationship x is square of y cannot establish any relationships where some elements of y may be square of elements in x. Here x is the first set and anchors the relationship. The second set in a function is the codomain. Codomain is the permissible valid values that outputs can be. For example, for the function sin x, the domain is all the real numbers, but the codomain is all the real numbers between -1 and 1. The value of sin x oscillates between -1 and 1. However, it should be known that a codomain is not necessarily dependent on input or domain. That is, it is not necessary that there has to be an input value in domain for the codomain to have the corresponding output value. For example, any function defined over real numbers in domain and codomain will have all the real numbers in the codomain irrespective of the actual values in the domain. In case you're still thinking about the fate of the actual output values or the potential output values, take it easy. These are called the range of a function. Range is a subset of codomain values. The picture shows the relationship between codomain and range of a function. And the relationship between domain and range is best brought out in the following statement. If the range of a function is a subset of real numbers, then it is called a real valued function. And if the domain of the function is a subset of real numbers, then it is called a real function. Graphs need a special mention. Graphs are like the twin of functions. Functions are extensively graphed. It helps in best understanding of the specific nature of functions. The four graphs showcase how graphs are central to really appreciating functions. To bring this lesson to a close, it must be emphasized that functions are how most mathematics is harnessed. All of algebra, geometry, calculus, topography, etc. is on the back of functions. Hope you would not be surprised that the next foundational lesson on relations and functions is on fundamentals of graphs and graphing of a few functions. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.